Trig Substitution Part 2, Substituting with Tangent. Recall that the integral of dx over a squared plus x squared is 1 over a times the arctan of x over a. So what if we have an integral that looks sort of like it? Let's try this one. Let's do the integral of dx over x squared times the square root of x squared plus 4. I don't see any other simpler techniques to use. It sort of has the form of our arctan in that I have an a squared plus x squared, in this case 2 squared plus x squared. So my mind goes to trig substitution with the substitution tangent of theta equals x, or x over 1. Just like we did with sine substitution, let's build our right triangle. If tangent is x over 1, I know tangent is opposite over adjacent. And then we would end up with x squared plus 1 as our third side. Now what I really wanted was x squared plus 4 somewhere to show up on my triangle. I realize I made a mistake, and instead of doing x over 1, I should have chosen x over 2. By Pythagorean theorem, my third side becomes square root of x squared plus 4, which is what I wanted. So now we do a substitution using tangents and other things. So back in my integral right there, we need to substitute every x for something with theta. Let's start with our dx, and I'm going to rewrite x first as 2 tangent theta, which means dx is 2 secant squared theta d theta. It also means that x squared is 4 tangent squared. And I wanted an x squared because it's in my integrand. So I've taken care of the top, the dx, as well as the x squared. I'm only missing the square root of x squared plus 4. And from my triangle, I see that the square root of x squared plus 4 over 2 is secant theta. Which makes me happy because tangents and secants go together. Really, tangent squareds and secant squareds go together. And then I'll rewrite square root of x squared plus 4 as 2 secant theta. And now I'll substitute into my integral. So dx is 2 secant squared theta d theta. X squared is 4 tangent squared theta. And then square root of x squared plus 4 is 2 secant theta. And let's see if we can simplify that integral a little bit. We can, of course. I can cancel out a 2 there. I can cancel out a secant top and bottom, which gives us secant of theta over 4 tangent squared theta d theta. Now there are different ways to handle this one. I do have a tangent squared, which could be rewritten in terms of secant squareds, but I think instead of doing that, I'll just try to change everything to sines and cosines. So I'll move this 1/4 out over here. And then on top, I have 1 over cosine theta. And in the denominator, we have sine squared theta over cosine squared theta. Looks like I can simplify this one down a little bit. And if I flip and multiply the denominator, I will end up with cosine of theta over sine squared of theta. Okay, that's a lot of work to get down to this. And I still need another technique to solve it, which is going to be a u substitution, where I'm going to let u equal sine of theta, which means du is cosine theta d theta. And if I plug in, I will now move the 1/4 outside of my integral, and I end up with du over u squared. Which gives me negative 1/4 times 1 over u. The negative came from the integral of 1 over u squared plus c. Well, now I got some back substituting to do. U is sine of theta, so 1 over u is the cosecant of theta. I'll repeat that. Since u is sine of theta, 1 over u is cosecant of theta. And I got to go back up to my triangle here. And know that cosecant is hypotenuse over opposite. So if I back substitute there, I end up with negative 1/4 times the opposite, so on the bottom, and the hypotenuse on the top, plus c. Slide back so we can see it. Hypotenuse over the opposite, and that is our antiderivative. Let's take a look at one more example. What if we had something like this? Now this looks like arctan. If it was just x on top, it'd be u substitution. So you might think this is a trig substitution with tangent, which will work. But we really, really want to see the easiest way to do things if whatever possible. So here's a little trick for you. If I add 1 and subtract 1 on the top, we add 0, which doesn't change anything, doesn't change the expression. But this allows me to rewrite my integral in the following way. I'll do this extra step so we can see where it's coming from. we can split up a numerator in a way that we like. And then simplifying, we get all this goes down to the integral of 1 minus 1 over x squared plus 1. And we should know the antiderivatives of these without doing any work. So if you would like to try, you can do trig substitution on this one and see that you get down to this. But I always want you to look to see what is the simplest way to do things.